All right, so let's consider the mechanism of the following reaction. Let's imagine that we have this alkene, and we are going to react this with HBr. Remember, our mantra is that the most reactive nucleophile makes a bond with the most reactive electrophile. So the first step is to identify the most reactive nucleophile and the most reactive electrophile. A couple of things to keep in mind is, number one, the HBr bond is really polarized. Bromine is more electronegative than hydrogen, and so bromine will have a partial bromine will have a partial negative charge. Hydrogen will have a partial positive charge. This means that the hydrogen is the best electrophile. And in all of these reactions with alkenes that we call electrophilic addition, the nucleophile will be the pi electrons in the carbon-carbon double bond. So in our first step, pi electrons will attack the hydrogen atom. Remember, tip of the arrow is where the nucleophile electrons originate. Tip of the arrow, two-headed arrow, means two electrons move. And of course, it's going to point to the atom that has the orbital that's deficient in electron density. Hydrogen cannot make two bonds, so it gives up its electrons to the bromine to form bromide. And a carbocation. Now here we have an interesting choice, because we can put the carbocation on this atom or on this atom, but if it's here, I'm setting up the possibility for a rearrangement to give a tertiary carbocation. So this is where it's going to go. And of course, we've made a new carbon-hydrogen bond. This mechanistic step, anybody want to tell me what it is? How would I classify what I just did? What kind of mechanism is this? This first step.
Isn't it a proton transfer?
Yes. I just enjoyed your pause there, Carrie. Very good, Carrie. Proton transfer. Absolutely right. You're simply transferring a hydrogen from one molecule to another molecule. Perfect. Okay, now in the next step, I have a secondary carbocation, but I can make a tertiary carbocation if I rearrange. So hydrogen and its electrons will undergo a 1-2 shift to produce a more stable carbocation. What mechanistic pattern is this? Anyone? This undergoes a 1-2 hydride shift. So above the arrow, I could even do 1-2 hydride. It's a, gosh, you guys are so smart. A 1-2 hydride shift. I go from having a secondary carbocation to a tertiary carbocation. I get more orbital overlap. It's lower in energy. So at this point, I have the most stable carbocation that I can have, and I have bromide ion in solution. And of course, this second step, rearrangement. So I have a positive charge in solution. I have a negative charge in solution. What makes sense as to what should happen next in our molecular movie, in our plot, in our story? You know, Michelle, that's not a bad thought at all. We have something with excess electron density, which is the bromide has excess electron density, so it is going to form a bond with that empty p orbital of the carbocation, which yields the final product. Now, let me ask a question. What is this mechanistic step best characterized as? What we did right here.
Loss of a, not loss of a leaving.
Oh, you caught yourself. That's good. It's not loss of a leaving group.
It's not loss of a leaving group.
Which step are you talking about?
The one.
Where the bromide attacks this carbocation. It's nucleophilic attack. Begu, begu. Nucleophilic attack. Now, not everything's going to have a rearrangement, but every time we do an addition reaction, and y'all put me to the test on this, it will have a proton transfer step and a nucleophilic attack step. It won't always be in this order, but those will always be there. You will always have these two patterns. All right. You guys like to overgeneralize things. Every student does, right? So let's overgeneralize. When you have electrophilic addition, these two patterns are always going to be there. Put that to the test when we do all these mechanisms in class tomorrow. So let's consider what the potential energy diagram might look like. So again, we are going to graph free energy as a function of reaction progress, the reaction from beginning to end. So at the beginning of our reaction, we have the energy of our reactants. So typically what I do is I just draw these. So I have HBr and I have my alkene. Now, the first thing that happens in this mechanism is, and I'm just going to call this ring an R group for simplicity. Is I begin to break this pi bond. I'm in the process of breaking it. And I am going to remove the hydrogen that is now beginning to lose its electrons to the bromine. The bromine has a partial negative charge, and of course, this is in the process of becoming the carbocation, so it will have a partial positive charge. First intermediate I form is when I have made the carbocation intermediate. And carbocation intermediate is right here. So we have the first transition state, the first intermediate. This is going to be the slow step of the reaction because I'm generating the most unstable carbocation. So this energy of activation has to be the highest. Second step is when I have my rearrangement. And when I have my rearrangement, now I will draw the ring. the hydrogen's beginning to break, and the hydrogen's beginning to make. Again, this is occurring transiently. So let me just blow this up a little bit. When I am doing a rearrangement, so of course this is more highly substituted. This is the carbon-hydrogen bond that is beginning. Actually, let me do this right. Yes, I am the greatest American hero. Thank you very much. That's Brian. You're an idiot.
Hey, no, hold on, hold on. There. I was gonna play it for you because I figured it's been a long time.
Ladies and gentlemen, YouTube world, I have an idiot in my class. So that's how I show the rearrangement. And of course, the next intermediate will be the most stable carbocation. The last transition state will be where I make the carbocation bromine bond. The bromine will have a partial negative charge. The carbocation now is going to be a partial positive charge because I'm in the process of alleviating that positive charge. And of course, at the end, I will have my products. This will be my delta H, or excuse me, my delta G of reaction. It's exergonic. The reaction releases free energy. It's exergonic. Of course, I can label my other activation energy barriers. Notice that the first one has the largest one. And so this is my slow step. And now I've completely mapped out this reaction with a potential free energy diagram. All right, so let's do another example. We have 1 butene and HBr in a reaction vessel. So my question is, what's our mantra? That's my first question. What's our mantra? What's our motto? What's our theme? What's our rally cry?
What is the most electrophilic?
Okay.
And
So we want to identify the best electrophile
and nucleophile.
and nucleophile. So, Michelle, what's the best way of identifying the best electrophile? What is an electrophile?
That's why I get twisted in.
Electron loving.
It's electron loving. So, Carrie, what does that mean in practical terms? If it's electron loving, what does that mean? What do we always want as humans? What we don't have?
Yeah.
So if it's electron loving, it's deficient in electrons. Now let's be even more practical. That means the electrophile should have one of 2 criteria. It either has a partial positive charge or an integer positive charge. So, Breland, of all of my molecules in yellow, which atom has the most electrophilic character?
The hydrogen?
I agree. Partial positive charge, partial negative charge because of the electronegativity difference. Have I talked to you guys about Fonkelbrish in class? Okay. So you can use that mnemonic, and it's real helpful in organic because we see these elements over and over and over in organic reactions. And it gives the descending order of electronegativity for the 9 most electronegative elements on the periodic table. Anything to the left is more electronegative than anything to the right. So notice that bromine and hydrogen have a relationship. So here's more partial positive, here's more partial negative. So this is where I get this relationship. That means that hydrogen is my best electrophile. Jessica, where's my best nucleophile?
The bromine.
If that's true,
No, because they together, no. It's
right,
the pi
it
bond.
wouldn't be the best nucleophile because they're already bonded.
Yeah, the pi bond.
And what did we say in electrophilic addition the best nucleophile is always going to be? It's always going to be the pi electrons. Okay. Is that feeling a little bit more natural now? Okay. So, Carrie, tell me what's going to happen in terms of pushing an arrow in this first reaction.
So, the hydrogen, we're going to draw an arrow from the well, no, actually, I'm sorry. We're going to draw an arrow from the nucleophilic pi bond, and we're going to draw an arrow to the hydrogen.
What does the tip of this look like?
It's a double-headed arrow.
Anything else happen?
Yeah, you're going to break the bond between the H and the Br.
So how do I push
You're
that
going to
arrow?
draw an arrow from the bond to the Br. A double-headed.
Now, I want to say a couple of things. I've seen you do it, and I've seen you do it. And normally when I point something out, it's something that you screw up, but you did something well. You started out incorrectly, and you corrected yourself. It's very good. So you're thinking about what you're doing, and that's good. This should hopefully start to breed more confidence that you can initially say something that's wrong, and you can correct yourself. I mean, don't we as human beings, isn't that like one of our fundamental principles? If we F up, we can be sincere, try to make it right, and you move forward, right? And so I like the fact that both of you all have done that, so that's really good. Now, Michelle, what should my products look like? Or my intermediates, I guess I should say.
It would be that butane without the double bond.
Where's the positive charge going to be?
Oh, onto second carbon.
A secondary carbocation is more stable than a primary carbocation. And what else do I have in solution at this point?
Br.
I have Br minus. Breland, what is the best mechanistic pattern to label this process as that we've just done? There's 4 of them now, right? And are we seeing these over and over? That's what I want you guys to see. That's why I teach the pattern before I teach the mechanism. So, what have I done in this reaction from the most simplistic definition? So I got on you guys earlier about not being sophisticated. Now I want you to be very unsophisticated. What have I done, Breland, in this reaction so far? Don't be sophisticated. And let me suggest this. You guys are going to look at your notes. You need to look at them less and less and less. So let me ask you a question. On a very elementary level, have I taken a hydrogen from one molecule to another?
Yes.
What is the best words to describe that?
I would say proton transfer.
Proton transfer. So more fluid with more confidence. This is a proton transfer. In fact, if you guys remember, I told you that electrophilic addition will always have two mechanistic steps, not necessarily in that order, and one of them is a proton transfer. Brian, what's going to happen next?
Now you're going to you're going to lose one of the pairs on the BR.
Okay, let's clean that up just a little bit.
You're
You're saying
transfer.
you're saying that one of the lone pairs of bromine is the most reactive.
Electrophile.
If it's an electrophile, it's electron loving. If it's
Yeah,
electron loving, what the hell is it doing donating electrons?
Nucleophile.
Nucleophile. This is our Bill Gates. It's got an excess of density and it's going to donate them. What's our best electrophile, Carrie?
What did he say? The best electro.
Shut the hell up. She didn't do that to you.
No, I'm just helping.
You're next, Breland. Electrophile means it's deficient in electron density, right? So there's no atom more deficient in electron density than one that has a positive charge. Remember, we defined up here earlier, the electrophile should always have a partial positive charge or an integer positive charge. This one has an integer positive charge. Just so we're clear, she beat you in the last test, okay?
I know.
He was showing me something worth looking at.
He's dirty minded.
I know.
He is dirty minded.
Seriously.
I didn't say anything. And we're done. So we don't always have a rearrangement. But we always, in an electrophilic addition reaction, have a proton transfer and a nucleophilic attack.